Hi everyone, my name is Vikram Sreekanti. I am a software engineer in the AMPLab at Berkeley, like Shannon mentioned. And I'm going to be talking today about some of the work we're doing over at Berkeley focused on metadata management, building metadata services, and why we think this is important and valuable. Before we get there, I'll start by talking a little bit about what data is, right? So in the 20th century view of data was sort of an accounting, right? It was a recording of the facts. So for example, you might say on February 16th, Sally withdrew $100 from her checking account, right? 21st century data, we look at data a little bit differently today. We might have a combination of facts like Sally's online purchase records, time series data from her Fitbit, popular films for various demographics, and the weather forecast for the next 48 hours. And depending on who you are, what service you're providing, what information you're trying to glean, you may combine these pieces of data in different ways to learn something different about Sally, right? So that's sort of how data has changed in the last 20 years or in this century. And the same thing we can say has happened with metadata, right? So metadata used to just be data about your data. You have a database table, and your metadata was the schema. It was really simple. Metadata today is a little bit different. So here we have an Apache weblog, right? And well, what's the metadata here? That's kind of up to you, depending on what you're doing, what you're interested in. You may extract different data and different metadata from this, right? And this is what a lot of people today call schema on use. And schema on use is one of the changes that's sort of taken place in the big data space in the last 10 or so years. But there are other things that we think are valuable to derive or perhaps find on use, right? So here are a few areas perhaps where we feel that metadata is really important and valuable. And this list is by no means exhaustive. We're not trying to say this is all the metadata that exists in the world. But these are some places where we feel metadata could be useful or really educational. So the first one is analysis, and I'm sure many people in here have seen a workflow that looks something like this. You have some data, you wrangle it, analyze, visualize, get some results. There's some feedback loop. Obviously, nothing's perfect the first time, and so on. What really gets written down today is the input data and the output data. And everything in between is sort of forgotten, right? We may put our scripts in a GitHub repository or something like that, but we're not really keeping track of which particular Git hash of the script was actually ran on which version of the data and generated which version of the results, right? So this is what we might call meta-amnesia. And Turing Award winner Jim Gray famously said, one of the things my research advisor Mike Harrison taught me to do was to write things down. And we think that that's really valuable and really important. And at the same time, on the right here, we have Monica Rigatti, who's a famous, well-known data scientist in the Valley. And she's at work here analyzing, wrangling her data. And something that she might say in response to that is, well, while I'm in the flow, so to speak, of doing my work and analyzing this data, it's kind of hard to stop and write things down, right? There's sort of an inherent tension between this idea that we should write things down and being in the flow of doing your work. But at the same time, we want to be able to capture the information and the insight that data analysts and data scientists have while they're doing their work, because no one in your organization and your future self won't know the data as well as you do while you're in that moment doing the work, trying to figure out what's going on with your data, right? So as we've been sort of thinking about this problem and designing a system, we've been talking to some of our friends at the data infrastructure team at LinkedIn, and something that they've said to us is, write down what you can and we'll fill in the rest. And this is, we think, a really important addendum to Jim Gray's quote, because obviously it's not possible to write everything down. And in 2016, we have much more computational power than we did 20, 25 years ago. And we have other tools like crowdsourcing or human curation that can help us take what we've written down and then figure out and augment that data later, right? Let's take an example here. I watch a lot of football. I'm a big football fan. And I'm sure if any of you watch football, you're familiar with these sort of these manual annotations that commentators and coaches will use while players are watching tape to say, like, okay, these were the routes that the wide receivers were supposed to run. And this technology we've had for quite a while now. Something new, though, is starting this past season, the NFL actually put motion sensors in the shoulder pads of every NFL player. And this is really cool, right? We're writing some stuff down. Automatically, you can record where a player was on the field, how fast they were moving, what direction they were moving, and so on, right? And then, it's not too far-flung to imagine, what if we took this metadata that we're writing down about where the players are on the field, how they're moving, and what if we combine that with a video game like EA Madden NFL? Then what we could do is we can take the quarterback, we can put him back in the pocket, he can look at, okay, I made this pass, but this other player was much more wide open, I should have passed to him, maybe I should look that way next time, right? And this is sort of the same thing, right? We're writing down what we can. We obviously can't capture everything. We can't capture where the quarterback was looking or where one of the defensive players were looking at things like that. But we can capture certain things. We're writing them down, and then we can fill them in later. And we think this is what should be done in the data analysis community. Capture what people are doing with data, augment it automatically as needed, and then when you go back, when you're trying to derive insight from it, then you interpolate appropriately. So this is what we might call metadata on use. Right? As we're using our data, as we're wrangling and analyzing and so on, we're generating this metadata that we're recording. The second use case is interoperability. So here we have a visualization from Tableau, and on the right you see drop call percentages by state for a particular telco. And on the left there's a scatter plot that shows you the subscribers' age in years and their call success percentage. And the orange color tells you whether they've dropped, and green says that they're still active. And there's an obvious correlation. Younger subscribers who have a higher drop call percentage tend to cancel their service. But we also see that there are some points at the very top and the very bottom here that don't necessarily conform to the rest of the distribution that we found. Well, something the user might want to do is go back upstream through the analysis pipeline and say, okay, where did these particular data points come from? Right? And let's say this particular workflow was using Trifacta to do the data wrangling. So there was a call detail file that came from HDFS. Trifacta did its analysis. The results were written back to Hive, and then Tableau read that and did the visualization that you guys just saw on the previous slide. Well, what if we could go back, take a step further back and go into the Trifacta UI, right? And we can say, okay, well, in this particular case, we found there's this data here in the contract end histogram, and there's some correlation with the subscriber age, and then we can look at the actual data points, perhaps, that we circled in the Tableau visualization, and perhaps clean our data or try to understand why those points that didn't correspond to the rest of the correlation that we found, why did those data points occur, right? In understanding these relationships and perhaps recreating them, there's a lot of different pieces that go into this, right? So we have our call detail file from HDFS and perhaps some master data on customers. We have the data wrangling script, which is, in this case might be in Trifacta's Wrangle language, and then we have a churn analysis that uses Python, right? But if we care about recreating something like this, we actually have to be able to say not just that these particular files were used in this way, we also have to be able to say, this version of this file was the particular input data that I ran on, and I used this version of NumPy and this version of my churn analysis and so on, right? Because with changes at any one of these places, you might end up with different results and not be able to recreate the relationship. So this sort of collaboration, or perhaps this interoperability between Trifacta and Tableau is one example that we can give and say, hey, this would be cool. But on the right here, we have the big data landscape for 2016, and every one of these logos is a company that's providing some service in the big data space, right? And for every one of these companies to build a connector with every other one of these companies in order to allow this sort of interoperation is completely infeasible, right? That's n-squared connections. So what we think is really important is having a shared place to write it down and to link it up. And when you do that, you can then allow all sorts of interoperation that won't necessarily be tied to any particular company or any particular partnership. So this is what we've termed standards on use. As you're using your data and as you're running it through a pipeline, you want shared standards to emerge that allow these pipelines to interoperate and work together. The next use case here is interpretation. Let's take a case with a recommendation system like Netflix. So in this system, we have some data, which will be user views and ratings and movie features, and we have a statistical model. And for any piece of data, for example, Sally watched The Shining, this piece of data is much more meaningful in the context of a particular model, right? Because the model is probably what made that recommendation. But the model is also not very valuable without the data, because the data is what's used to train and refine the model that we're using. So any interesting machine learning system has this coupling, and the key insight here is that neither the model or the data really have any value without the other. the interpretation of the data depends on the model, and the models are parameterized correspondingly by the data. So there's this sort of feedback loop, right? And in this case, and with any of these machine learning systems, or perhaps these model-based systems, what really is valuable is understanding the data and the metadata on use. In order to be able to understand these systems and recreate some of this behavior, we need to have both the data and the metadata. So, some of you might be saying, you guys think metadata is super cool, it can do all these great things. Can metadata cure cancer? Well, no, it can't. But it's also going to be really, really useful in curing cancer, right? So I'm going to talk a little bit about a use case that we've gotten from our friends at the Cancer Genomics group over at Berkeley. And they're doing some really great work with leukemia patients where they have this patient data. They're doing this sort of join algorithm that compares it with a commonly used data set in genomics called the 1,000 genomes data set. And then they run some sort of clustering algorithm to find the similarities and the differences between some of the leukemia patients and some of the people in the general population. And so they can perhaps find markers that indicate when leukemia or other diseases are more likely to occur. And then they have their publications. They create science. But if we want to recreate something like this, we really have to go all the way back. It's not just the code that we're running. It goes all the way back to the physical cells and the tissue, right? So in an example like this, something that might happen is we put leukemia cells on a slide. And these slides have barcodes. So they all have unique identifiers that we can refer to. And once we have the cells on the slide, the robot will put some chemicals on the slide to prepare them for sequencing. And then we put the slides on a gene sequencer. And this happens for thousands of patients. And then we run the code where we do the join algorithm with the general population data, the clustering algorithm, and so on. So in order to understand a workflow or a process like this, we really need to be able to go all the way back to the tissue, figure out which barcode generated which sequence of genes and which piece of code was ran on that, make sure that perhaps the versions of code that was running on the gene sequencer and also the clustering algorithm, et cetera, make sure that all of these sort of conform or are the same in order to reproduce this. And this is something that's really valuable in the scientific community. A lot of people that we've talked to have said, look, and there's a lot of criticism about not being able to reproduce results. So if we can have something like this where we can write down every step of the process, track everything, and then keep it in one place, that'd be really, really valuable. And we think that's something that's useful not only in science, but also in the real world and in real use cases. But it actually gets even messier than that, right? So this clustering algorithm that they use, just with most machine learning algorithms, has a bunch of parameters and knobs that you can tune, right? And another criticism that we've heard is a lot of scientific research, they get a graph by tuning the parameters to a few specific parameters. They get that graph, and then they run away. They're like, don't touch the knobs. This generated the graph that's in my report, right? But that's not necessarily what good scientific research entails. And a lot of times they run parameter sweeps over these parameters, right? Have a computer run every possible combination of these parameters, and then we can look at the statistical distribution and say 95% of the time the results correspond to my hypothesis, and in these 5 cases they don't because of X, Y, and Z, or something like that. We need to be able to write down not just this particular barcode, but this particular barcode with this particular set of parameters generated this result, right? And being able to reproduce on this scale, we think is both a very challenging problem, but also a really interesting and valuable one to solve. This is what you might call lab notebook on use, right? This is what good, meticulous researchers do in the first place. They write down everything they've tried, make sure it's organized, and make sure they can go back and refer to it later. And we want to do that automatedly, right? We want to be able to be the lab notebook for these use cases that already might be doing something similar to this. The last use case we have here is governance. And governance is one of the first words that comes up whenever you mention metadata, right? And at the same time, we understand that there's perhaps a little bit of a tension between the idea that folks in the IT department want to be able to audit and prevent incorrect access of data, make sure that you're complying with HIPAA or any other regulations that there are on the data. But with this, if you'll excuse the cliche, so-called democratization of data, a lot of data scientists want the ability to be able to get their hands on the data and to wrangle it, analyze it, do whatever, and find their insights from it, right? So this this tension is something that we're aware of, and it's sort of an open question for the community to answer, but we think there's some interesting insight we can offer. There's a project over at Berkeley called the Jupyter project, right? And what they started off as the IPython notebook project, and what they have is sort of like an electronic lab notebook, right? So you can write some plain text in Markdown, you can write some, originally it was Python, but now you can write one of 50 or 60 different languages. You can press enter, it'll run the code, you see the results, and it sort of scrolls down. You have this nice history of everything that you've done, things that you've tried, how your thought process has changed, and so on and so forth. This is something they've been doing since 2011. And as the project has matured, something a lot of professors at Berkeley have done is they've started running classes out of these Jupyter notebooks, right? So give you a quick overview. Every assignment is a notebook. You sort of leave some blanks where students need to fill in answers or to write some code. And every student creates a version of this notebook, and that version becomes their submission of the assignment. And the staff solution is another version. So in order to grade these, you execute every notebook on some data, annotate them with grades so students get some feedback, and you update a master grade spreadsheet, right? But as with everything, there are some rules that we have to follow. So, and there's some basic rules. Students shouldn't be able to see each other's homework. They can't see the solution unless they've already turned their homework in and it's after the due date and they have a Berkeley login. And we hire other undergraduates to grade students' homework, so graders shouldn't be able to see the students' names because you don't want them to be biased towards their friends, but they should be able to see the solution, so there's some perhaps fine-grained access control beyond just they can see this file or they can't. And then obviously students shouldn't be able to update the grade spreadsheet, or that'd be kind of bad. I mean, these are school-specific rules, but we think that these are analogous to a lot of the rules that exist in industry and with other problems that people have. These sort of access control, access rights, restricting what you can execute code on, and so on and so forth, we think is analogous to what people are doing in industry. But we also think that rules should be a small part of school, right? We think that if people do things well, then it allows people, software, and organizations to get smarter. So let me give you a quick example. Let's say that every student is working on this assignment, and we have a message board that we have for all our classes where students post questions and either instructors or other students answer. We teach really, really big classes, so it's kind of hard to have instructors answer every single question. But the idea is, let's say a particular student is struggling with a question on the homework. They've tried it 5 or 6 times. They can't seem to get it right. Well, if we're able to capture some of the metadata around what people are doing, what questions they're looking at on the message board, how long it's taking them to get questions right, then maybe we could say something like, hey, you're having trouble with this question. Maybe go look at this post on the message board that 25 other students looked at, and within 5 minutes of looking at this question, they were able to get the right answer to this particular exercise, right? And that also helps us as instructors learn, look, you're not teaching this concept well. Everyone's really struggling with understanding B-trees or file systems or something like that, right? And that helps us improve our teaching and the way we're doing things. So it's not just writing down metadata, but it's also helping us as an organization get smarter. And we think that this all comes back to writing things down and filling them in later. Because if we're not writing down this metadata, if we're not keeping track of who's doing what or how they're doing it, then we're not able to generate this kind of insight. So there's a blog post from Michelle Getz from a few months ago. I'm not sure why the URL isn't showing. It was on Forrester. And I'm paraphrasing a little bit here, but we're missing a few words here. But basically the idea here is this. If you give everyone access to your data, maybe they can't change it, but they can look at it and they can annotate it. Then what you get is people saying like, hey, this data is really useful for this particular use case, or hey, this data looks kind of skewed, it doesn't look right, right? And that sort of encourages a reuse of scripts and data cleaning, these kinds of things, and also fosters some debate because different people may have different opinions on what the correct version of the data is or what a meaningful version of this data is. And as we foster this debate, we hope that this leads to a consensus about what is a correct version of the data or a correct version of the data for a particular use case. And as we see at the bottom, collective intelligence emerges, right? We think this is governance on use. As you're using your data, as you're analyzing it and wrangling it, as I've said about 15 times now, you can, the governance and the understanding of what's correct and what's well-formed and all these things sort of emerges out of this, this idea that we are iterating over governance and understanding what is correct, right? So what are we actually doing? Well, we're trying to build a system around this stuff that can capture this stuff and represent it well. We're trying to focus our design on useful and interesting problems. One of them that we're focusing on is the cancer genomics use case that I mentioned earlier. We're trying to facilitate some of the reproducibility work they're doing. And at the core of what we've done over the past few months has been developing what we hope is a general but expressive data model, right? We don't want to be prescriptive. We don't want to tell people how to store their metadata or what kind of metadata they should be storing. That's up to them. But we want to be able to support as many different kinds of metadata as possible while still being useful, right? So I'm going to spend a couple minutes talking about the data model that we've developed and some of the principles underlying it. So at the very core of this data model is right now what we're calling a thing. And the idea behind a thing is that it's immutable. Everything has a version history. If you update it, you never overwrite an old version. You actually create a new version, right? It's fairly simple. And we think that this facilitates sort of understanding these relationships, like I was talking about earlier, right? Because if you are, like, so for example, take HDFS, not an inherently versioned system, right? But in order to be able to reproduce this, we need to know exactly which call detail file we were looking at in HDFS, right? And the same thing with a lot of master data systems. They're not necessarily versioned. We may have master data by date or some other metric, but we need to understand all the versions of these things, including our Python scripts and what version of NumPy and so on and so forth, right? And then if we can do the reproducibility, the next thing we can do is go back and look at alternate histories, right? What happens if we keep everything else the same, but we change the call detail file? Then what does our churn analysis say? Do we think that we would have had better subscriber retention, or would it have gotten worse, or something like that, right? So, and then we can use that to actually compare against real data and then say, like this was good or this was bad. We did a good job here or something like that. The next layer of our data model is the Mantle. And the Mantle sort of is where the user starts reasoning about things. So we have some basic constructs. We have nodes, edges, and graphs. Nodes are standalone things. Edges represent relationships. And graphs are just sets of edges, right? So however you want to model your data, even if you want a bunch of standalone things, you can just create a bunch of nodes. The edges represent relationships, and so on and so forth, right? And the outermost layer of our data model is the Crust. And the Crust sort of helps us represent the lineage relationships between things, which brings me to one of our next design principles, which is the fact that lineage is fundamental to any metadata system, right? Versions help us track who did what, when they did it, and so on. But what lineage helps us track are sort of causal relationships between things. So we can say, hey, we have dataset B. It's the logical descendant of dataset A, and we ran workflow 1 on dataset A to generate dataset B, something like that, right? And a couple of the other more general design principles that we have, one is Postel's law. So John Postel was one of the pioneering designers of many internet protocols. And something that he famously said was, be conservative in what you do and be liberal in what you accept from others. So we don't want to make our metadata services very complicated or very prescriptive. We want to be as general as possible, and we want to let other people build things on top of our services to better facilitate their use cases. And the last thing that we think is important is the neutrality of this system, right? We think that it's imperative that a system like this be open source and vendor neutral. We don't want, we think that if this system were to be tied into any particular vendor's ecosystem, there would be, customers don't necessarily want to put their data in one particular ecosystem. That doesn't necessarily foster open interoperability and some of the other things we talked about. So we think it's really important. That's why we're doing this over at Berkeley. It's open source and vendor neutral. That's all I have for today. Feel free to check out what we've done. It's all open source on GitHub. And if you're interested or have any questions, feel free to reach out to me. Thank you.